Have you ever wondered if there are fundamental boundaries to what we can truly know about the universe, especially at its smallest scales? Imagine trying to pinpoint two elusive characteristics of something incredibly tiny at the exact same moment. What happens when our desire for ultimate precision meets the inherent nature of reality? The most profound limit to simultaneous quantum measurement precision is the Heisenberg Uncertainty Principle. This foundational concept in quantum mechanics states that you cannot simultaneously know certain pairs of properties, such as a particle's exact position and its exact momentum, with perfect, arbitrary precision. This limitation isn't due to faulty instruments or clumsy experimental techniques. Instead, it arises from the very fabric of the quantum world. In quantum mechanics, certain pairs of properties are called non-commuting observables. This means that the act of measuring one property inevitably disturbs the system in such a way that it changes the other, making it impossible to precisely determine both at once. It's as if measuring one quantity inherently blurs the other. This inherent uncertainty is quantified by Planck's constant, often represented as h-bar, a tiny but crucial value that sets the scale for these quantum effects. Understanding this principle means that when you are working with quantum systems, you must make a deliberate choice about which properties to prioritize in your measurements. For instance, in quantum computing, knowing the exact energy of a qubit might mean you have less precise knowledge of its phase. This forces careful experimental design and informs strategies for quantum error correction, where balancing these uncertainties is key to maintaining quantum information. Think of it like trying to perfectly photograph a moving car. If you want a perfectly sharp image of its location, you need a very fast shutter speed, which blurs its movement and makes its exact speed harder to determine. Conversely, if you want to precisely measure its speed over a time interval, its exact location during that interval becomes less definite. These complementary variables are intrinsically linked. It is not about the limitations of our camera, but a fundamental trade-off in what can be observed. Ultimately, the Heisenberg Uncertainty Principle is not a bug to be overcome, but a fundamental feature of nature itself. Embracing this inherent limit allows us to develop a deeper understanding of how the quantum world operates. It guides the development of technologies like quantum computers and sensors, reminding us that reality at its core is far more nuanced and dynamic than our everyday experiences suggest.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.